Hello friends, welcome to the video lessons on electronic measuring instruments. In today's class, I'm going to explain about the deflection sensitivity of a CRT and how to derive the deflection sensitivity expression and some simple problems on calculation of deflection sensitivity of a CRO we'll try to solve. But before going to the present topic, let us try to recollect what we have studied in the last class. In the last class, we have studied about the need for time-based signal, deflection amplifiers, and triggered sweep. Time-based signal is used in order to sweep the electron beam horizontally through the x-axis from left to right. Without time-based signal, we will find out only a luminous spot moving in a vertical line. We cannot see the exact wave shape of the applied input signal unless time-based signal is applied and the electron beam is swept through the screen from left to right. Then coming to deflection amplifiers. Basically, the deflection system in a CRO consists of two parts. One is horizontal deflection system, the other one is vertical deflection system. Vertical deflection system consists of a vertical amplifier followed by a delay line, and vertical amplifier is used to amplify the applied input signal. And horizontal deflection system consists of a trigger circuit, time-based generator, and a horizontal amplifier. Trigger circuit is used to convert the sinusoidal signal into a train of pulses, and sweep generator is used to convert a train of pulses into a sawtooth signal, and horizontal amplifier is used to amplify the sweep signal or sawtooth signal. Then horizontal input signal from the output of horizontal amplifier and vertical input signal from the output of vertical amplifier through a delay line are applied simultaneously to the deflection plates, so that both are applied simultaneously and we can see the entire cycle of the applied input signal without any loss of signal. Then coming to the triggered sweep. Basically, a sweep signal consists of a ramp, upgoing ramp, and a downgoing ramp. Upgoing ramp makes the electron beam to deflect from left to right. And in order to prevent the electron beam move from right to left due to downgoing ramp, the the ramp which is moving down towards zero has to be blocked. Otherwise, we will get a wave shape which is continuously moving, which is flickering in nature. So, in order to get a flicker-free waveform, a triggered sweep circuit is best suited for a CRO. Coming to the present topic, deflection sensitivity. We know that The deflection system that is employed in a CRO is electrostatic deflection, and deflection sensitivity is defined as the amount of vertical deflection of the electron beam on CRO screen per unit deflecting voltage. That is, when a unit deflecting voltage of the applied input signal is applied, how much the electron beam will move in the vertical direction. The amount of vertical deflection of the electron beam on CRT screen per unit deflection voltage of the applied input signal. It is expressed in centimeters per volt, and deflection factor is the reciprocal of the deflection sensitivity of a CRT. So deflection factor is expressed in the units of volts per centimeter. That is, the amount of voltage required, the amount of vertical input voltage required to cause a deflection of to cause a vertical deflection of 1 centimeter on CRO screen is called as a deflection factor. Now, let us try to analyze the deflection sensitivity of CRT assuming a single electron, whether it is a beam of electron consisting of n number of electrons, maybe n in the uh, amount of some lakhs of electrons, or a single electron. The concept would be the same. So let us try to analyze the concept using a single electron. First, the electron beam is produced by the electron gun. That is, the heater element heats the cathode and electrons are released from cathode. All these electrons are allowed to pass through a narrow passage which is coaxial with the CRT axis, and through this narrow passage electron beam will come out, and that electron beam reaches the vertical deflection, passes through the first set of accelerating anodes called as pre-accelerating anode, followed by a focusing anode, followed by an accelerating anode, a set of plates called accelerating anodes. This pre-accelerating anode and accelerating anode are maintained at very high positive potentials in order to increase the kinetic energy of the electron ejected from the control grid. And focusing anode is used to provide a double concave lens type of arrangement to make sure that the electron beam is converged and focused beam. Now, among that electrons in the beam, assume that the velocity of electron, either a single electron or a n number of electrons, the velocity of electron that is developed by the accelerating anodes be Vox, that is the initial velocity of the electrons passing through the accelerating anodes and reaching the vertical deflection plates. At the beginning of the vertical deflection plates, let the initial velocity be Vox in the x direction, and in y direction there won't be any velocity. In z direction also there won't be any velocity. Now there are two parallel plates with a potential Vd applied between them. These plates produce a uniform electrostatic field in the y direction, that is in this direction from top to bottom. The electric lines of flux, you can see the parallel uniform electric field from top to bottom. Upper plate is at positive potential compared with the lower potential. So electric lines of flux are directed from top to bottom plate, upper plate to the lower plate. Now, the electron, which is having an initial velocity of Vox, enters into this uniform electric field produced by the potential difference applied across the deflecting plates, that is plus Ed. Now, here you please see that the length of the deflecting plates is LD, L suffix D, and the distance between the two plates is small d. So the two vertical deflection plates are mounted horizontally at a distance of d centimeters, and the length of the deflection plates is LD centimeters. Now, there is no force either in x direction or in z direction. Hence, there will be no acceleration of electrons in these directions. Let EA be the voltage of the accelerating anode in volts. EA, that is the voltage applied at the accelerating anode, which is responsible for this initial velocity of Vox. And EB, the charge of electron in coulombs, and MB, the mass of electrons in kg. Now, we know that the because of the accelerating voltage EA applied across the pre-accelerating anodes, the electron or electron beam coming out of control grid loses its potential energy and gains kinetic energy. So the amount of loss in potential energy would be exactly equal to the amount of gain in kinetic energy. So what is the amount of loss in potential energy? So the amount of loss in potential energy is the product of the charge of the individual electron multiplied with the potential applied causing that loss of potential energy. So it is E multiplied with EA. Now, what is the gain in kinetic energy? Gain in kinetic energy is given by the equation. Velocity is gain in kinetic energy is half into mv square. That is the expression for kinetic energy. Here m is the mass of electron and v is Vox, that is the initial velocity of electron before entering into the field of vertical deflection plates. So ED is the potential difference between the plates, D distance between the deflecting plates in meters, LD is the length of deflecting plates in meters. We can go for either meters or centimeters, that is our choice anyhow. And of course L is the distance between the screen and the center of the deflecting plates in meters. Please see here. This is the center of the deflection plates from here to the screen. This length is given as capital L, and D is the deflection of electron beam on the screen in y direction in meters. This distance, starting from here to this point, the electron beam reaching the CRO screen hits the CRO screen at this point. That means instead of hitting the electron, the screen here, because of the applied electric field, it has moved away in the vertical direction and is hitting the surface of the screen here. So what is the vertical movement of the electron beam? It is nothing but d. The loss of potential energy when the electron moves from cathode to accelerating anode, E is equal to EA. Similarly, the gain in kinetic energy by the electron is half m VOx square, where m is 9.109 into 10 power 31 kg. Now, equating these two energies, that is, EA is equal to potential energy is equal to kinetic energy. That means EA is equal to half m VOx square. Now, equating these two, let me write it here. So, potential energy equated to kinetic energy gives the expression. This 2 can be taken to the left hand side. So, it is 2EA. M is brought to the left hand side. It will be in the denominator. So, it is 2EA by M. And VOx whole square is this one. When you want the velocity VOx, then it is square root of 2EA by m, or in other words 2EA by m power half. Yes, please remember this equation. The initial velocity of electron before entering into the field of the vertical deflection plates is 2 into E into EA by m power half, that is square root of 2EA by m. Now we know that according to Coulomb's laws of electrostatics, F is equal to 1 by 4 pi epsilon naught epsilon r. Actually, this is just a moment, please. Copy or else cut, paint, crop. This is simply epsilon. If you write epsilon naught, you have to write epsilon r also. Epsilon naught indicates the absolute permittivity and epsilon r indicates the relative permittivity. And epsilon is the product of epsilon naught and epsilon r. So this is the expression. F is equal to 1 by 4 pi epsilon into q1 q2 by d square, and E is equal to 1 by 4 pi epsilon q by d, and V is equal to 1 by 4 pi epsilon into q by d. The second one is q by d square, third one is q by d. Now if I interrelate these two, E can be written as F by Q, or F is equal to E into Q. Now V can be written as E by D. V can be written as, E into D. When you multiply here with D, you arrive at this expression. So E into D is equal to V, or E is equal to V by D. And V by D, as you can see here, can also be written as F by Q. Now using these relations, interlinking between force, field and potential difference, the electric field intensity in the y direction, we know that the potential in the y direction is ED. So what is the electric field intensity? EY is equal to V by D. In this case, here it is ED by D. Now force acting on an electron in y direction, Fy, 20 minutes. Fy is equal to E into Q here. So charge of electron into Ey, that is equal to E into Ed by D. In place of Ey, it has been replaced with Ed by D. Now suppose if Ay is the acceleration in y direction, then we know that force is equal to mass into acceleration. So the force applied in the y direction can also be written as mass into Ay, mass of electron into Ay, or simply Ay can be written as E into epsilon y by m. That is this one, Ay is equal to Fy by m, or instead of Fy it can be written as E into Ey by m. As there is no initial velocity in the y direction, the displacement y at any instant t in the y direction is, we have got the expression for this one, the acceleration. Now if we want to write the expression for displacement in y direction, for expression of displacement in a direction is qt plus half at square. Displacement d is equal to ut plus half at square, where u is the initial velocity, a is the acceleration, and d is the displacement. Here the initial velocity is 0, because in y direction there is no initial velocity. So when initial velocity is 0, the displacement is simply half Ay into t square. In place of Ay, I can rewrite Ey by m. So it is half E into Ey by m. In place of Ay, E into Ey by m multiplied with this t square, and this t square. Now as the velocity in x direction is constant, The displacement in x direction can be given by a generalized expression as x is equal to Vox into t. Displacement is equal to velocity into time, general expression. That is because in x direction it is linear. So we can write t, the expression for t from this as x by Vox. Vox is the initial velocity, x is the displacement in x direction. So let me rewrite this t with x by Vox in this equation. Then what the equation appears here now? Half E Ey by m into x square by Vox square. Half E Ey by m into x square by Vox square. The above equation is called as a parabolic equation. Now, just like this, here this is the path of parabola. Only up to this portion it is parabolic in nature. After that it would be linear. Now, in this parabolic path, if I find the tangent, then I can conveniently find out what is the value of d simply by extending the line by identifying the slope. So here what happens, the slope at any point xy is given by the equation for the parabola dy by dx is equal to this expression y is differentiated with respect to x, that is d by dx of y. Now if you see on the right hand side, except for x square, all the remaining terms are constant. So you can write this as d by dx of y is equal to 1 by 2 Ey by m V0 square into d by dx of x square. We know that d by dx of x square is 2x. So if I write that 2x in place of d by dx of x square here, then d by dx of y is equal to, in place of x square it is 2x, and 2 in the denominator and 2 in the numerator get cancelled out. So d by dx of y is equal to E epsilon y into x, E Ey into x by m V0 square. E Ey x by m V0 square. This is the slope. Now let me take the slope at exactly at the point of leaving here. At the point of leaving, let me note down the slope of the curve. Now, when you put x is equal to LD, that means this one. The electron beam is moving in this direction. At the same time, because of the applied field, it is moving in this direction also. Because of this applied electric field in the y direction, the electron beam is following a parabolic path. So we know the general expression for slope of this parabola. Now by applying the value of x as LD, that is exactly at the point of leaving the deflection plate assembly, vertical deflection plate assembly, the slope would be x equal to LD. In the above equation, we get the value of tan theta. Then tan theta is equal to E Ey, in place of x we write it as LD by m Vox square. So this is tan theta, that is the slope of the parabolic path of the electron beam at the point of leaving the vertical caused by the electric field caused by the vertical deflection plates. So after leaving the deflection plates, because there is no particular electric field which influences the path of the line, the electron beam, it travels in the straight line with the same slope as this. With the same slope as this, it follows a straight line. That is, from here afterwards, this is the slope, it follows the same slope. Now, following the same slope, now it has made an angle theta. This straight line has made an angle theta. Now, what is tan theta here? Tan theta is equal to d by L, or tan theta is equal to y by x. Just let us see further. The straight line of the straight line of travel of electrons is tangent to the parabola at x is equal to LT, and this tangent intersects the x-axis at point 0. That is, when you draw a tangent line here following the same straight line with the same slope, it intersects the x-axis at a point O. The location of this point is given by the equation, once again general equation, tan theta is equal to y by x, obvious simple equation. Tan theta is equal to y, either d by L or y by x. So x is equal to y tan theta. We know the expression for y at L is equal to, at x is equal to LD. So when x is equal to LD, y is equal to 1 by 2, this equation. When x is equal to LD, y is equal to 1 by 2 E Ey LD square by mVox square. That is y. 1 by 2 Ey LD square by mVox square. And what is tan theta? Tan theta is equal to, we arrived at the expression, E Ey LD by mVox square. Now, simply substituting these two, we know the expression for y at x is equal to LD, and at the same time we know the value of tan theta at x is equal to LD. So by substituting these two, we get the point of intersection of the straight line intersecting with the x-axis. That distance x is given by y by tan theta. Now please see here, this is y divided by tan theta. That means this, what we say, numerator becomes a denominator and denominator becomes numerator. In this equation, y by tan theta, if you write, then it is simply half E Ey LD square by m V naught square multiplied with m V naught square by E Ey LD. Now mv square both in the numerator and denominator get cancelled out. and E, Ey both in the numerator and denominator get cancelled out, and LD square in the numerator and LD in the denominator. So one LD also gets cancelled out. So the expression for x, that is the distance x at which the line or the tangent intersects the x-axis, is given as LD by 2. LD by 2. This is the total length LD. Now, where exactly would be the LD by 2? LD by 2 would be at the center of the length. So, this is the point of interest. Hence, the point of intersection O on x-axis is at x is equal to LD by 2. Now, the apparent origin is thus at the center of the deflection plates. Now, the deflection D on the screen is given by D is equal to L tan theta. Now, this is theta. From here, let us project this line, and this line or this tangent is making an angle theta with a horizontal axis, and tan theta is equal to D by, from here to here, that is the opposite arm. What is that length? That length is L, capital L. So D by L is tan theta. Tan theta is D by L, or D is equal to, that is the amount of vertical deflection is equal to L tan theta. Now replace the tan theta with its equation. The equation for tan theta is E Ey LD by M Vox square. So L as it is written, and for tan theta it is written as E Ed LD by M d Vox square. That is because Ey can be written as, yes, Ey can be written as Ed by d. So writing that here, for tan theta, L E Ey LD by M Vox square. Further elaborating Ey as Ed by d, the expression for d is equal to L into E Ed LD by M d Vox square. Now please see here, Vox square is equal to 2 Ea by M. This is nothing but the expression, the equation arrived at by equating the potential energy and kinetic energy. Ea is equal to half M V naught square, Vox whole square, half M Vox square. Rearranging that, we arrived at Vox square is equal to 2 Ea by M. Replace that Vox square with this equation. It is in the denominator, so obviously this ratio gets inverted. This fraction gets inverted. M comes in the numerator and 2Ea comes in the denominator. So when M comes in the numerator, M gets cancelled out with the denominator part M here, and E in the denominator gets cancelled out with the E in the numerator part here. So E and M get cancelled out, and the left out terms are 2EA in the denominator along with D. VOX is written separately, so left out are MD, out of which M got cancelled out. So in the denominator it is 2D into EA. Whereas in the numerator it would be LED LD. So the deflection on y-axis after a large number of manipulations, we arrived at the expression D, the vertical deflection of the electron beam on CRO screen, is equal to L, that is the distance between center of vertical deflection plates to the screen. ED is the potential difference applied across the vertical deflection plates. LD is the length of the vertical deflection plates divided by 2 into D. D is the distance between the two vertical deflection plates. EA is the potential applied at the pre-accelerating anode. So D is equal to LED LD by 2D EA. Now what is the expression for deflection sensitivity? Deflection sensitivity is defined as the amount of vertical deflection of electron beam for unit deflecting voltage. Here the deflecting voltage is ED. So because of ED deflecting voltage, we have got a vertical deflection of D. So for unit deflection voltage, that means sensitivity, if I write the symbol as S, S is equal to D by ED is LLD by 2D into EA. LLD by 2D into EA. Meters per volts or centimeters per volt. That is the expression for deflection sensitivity. So what about deflection factor, reciprocal of deflection sensitivity, and it would be 2dEA by LLD. G is equal to 1 by S is equal to 2dEA by LLD, volts per meter or volts per centimeter. So from the above equations, we conclude that the sensitivity can be increased or decreased by changing the value of accelerating voltage. The sensitivity can be increased by decreasing the accelerating voltage. Sensitivity can be decreased by increasing the accelerating voltage. Now, let us try to solve some simple example problems on the deflection sensitivity. The first example, an electrically deflected CRT has a final anode voltage of 2000 volts and parallel deflecting plates 1 centimeters long and 5 millimeters apart. If the screen is 50 centimeters from the center of the deflecting plates, find the following: beam speed, deflection sensitivity of the tube, the deflection factor of the tube. Let us try to look into the data given here. It is given that final anode voltage is 2000 volts, that is EA is equal to 2000 volts. The length of parallel deflecting plates is given as 1.5 centimeters. That is, LD is equal to 1.5 centimeters. And the distance between the two deflecting plates is given as 5 millimeters. So D is equal to 5 millimeter. Then, if the screen is 50 centimeters from the center of the deflecting plate, that means L is given as 50 centimeters. So with this given data, we have to find out the beam speed and the deflection sensitivity of the tube and the deflection factor of the tube. How do you find the beam speed? We know the expression for beam speed Vox is equal to EEA by m power half 2 EEA by m power half 2 into the charge of electron is 1.6 into 10 power minus 19. EA is 2000 volts divided by the mass of electron is 9.1 into 10 power 31 under square root. Now you can see 2 into 1.6 into 2000 by 9.1. Let us try to calculate this. 2 into 1.6 into 2000 divided by 9.1. That is equal to 703. Sorry, 2 into 1.6 into 2000 is equal to divided by 9.1 is equal to 703.29. And what is the square root of this? To find the square root of this, its value is 26.5. 26.5 is the magnitude multiplied with, value multiplied with 10 power minus 19 in the numerator, 10 power minus 31 in the denominator, minus 19 and plus 31 in the numerator. It is 12. 10 power 12 under square root is 10 power 6. So the velocity of beam is 26.5 into 10 power 6 meters per second. Then deflection sensitivity. Expression for deflection sensitivity is, we know it as LLD by 2D into EE. L is given as 0.5, 50 centimeters, that is 0.5 meters, and LD is given as 1.5 centimeters, so 1.5 into 10 power minus 2 divided by 2 into D is 5 millimeters, so 5 into 10 power minus 3 into 2000. So if you see here, 10 power minus 3 into 2000 is simply 2. 2 into 5, 10 into 2, 20. 20 in the denominator, 0.5 into 0.15 into 10 power minus 2. So the value comes out to be 0.375 millimeters per volt. You can do the calculations here for this. You can arrive at the result as 0.0375 millimeters per volt. That is the deflection of the electron beam on vertical screen, or else the vertical deflection of electron beam on CRO screen for unit vertical deflection voltage is 0.375 millimeters. Deflection factor G is 1 by S, that is 1 by 0.375, that is 2.66 volts per millimeter. That is, it requires 2.66 volts for to cause a vertical deflection of 1 millimeter on CRO screen. Second example, in a CRT, the distance between the plates is 1 centimeter. The length of the deflection plates is 4.5 centimeters, and the distance of the screen from the center is 33 centimeters. If the accelerating voltage is 300 volts and the deflecting voltage is 50 volts, then find velocity of electron reaching the field, deflection produced on the screen, deflection sensitivity. Given data is D is equal to 1 centimeter. Distance between the plates is 1 centimeter, written as 1 into 10 power minus 2 meters. Length of the deflection plates is 4.5 centimeters. That is 4.5 into 10 power 2 meters. L is equal to. Distance of the screen from the center of the plates is 33 centimeters. L is equal to 33 centimeters, or equal to 33 into 10 power minus 2 meters. Then accelerating voltage VA is 300 volts and deflecting voltage VD is 50 volts. Now first, to find velocity of the electron reaching the field, formula is quite simple. Already we have done one example. Vox is equal to 2 into E into VA by M. So 2 into 1.6 into 10 power 19 into 300 by 9.107 into 10 power 31. So the value comes out to be 1.0267 into 10 power 7 meters per second. This is the initial velocity. Then deflection produced on the screen. What is the expression for deflection produced on screen? D is equal to L Vd into L, that is Ld, divided by 2D into Va. So L is 4.5 into 10 power minus 2, Vd is 50, Ld is 33 into 10 power minus 2, divided by 2 into distance is 1 centimeter, that is 1 into 10 power minus 2, Va is 300. If you do the calculation, you will arrive at the result as 0.1237 meters. This is the amount of vertical deflection of the electron beam on CRO screen. And deflection sensitivity is nothing but vertical deflection divided by the vertical deflecting voltage. 0.1237 divided by 50, that is 2.474 into 10 power 3 meters per volt. That means the electron beam produces a deflection of 2.474 into 10 power minus 3 meters, or else 2.474 millimeters per 1 per unit vertical deflection voltage. This is second example. Another example here. In a cathode ray tube having electric deflection system, the deflecting plates are 2 centimeters long. LD is 2 centimeters and have a uniform spacing of 4 millimeters between them. D is 4 millimeters. Fluorescent screen is 25 centimeters away from the center of deflection plates. That is, capital L is equal to 25 centimeters. Calculate the deflection sensitivity if the potential of the final anode is 1000 volts in one case, 2000 volts in another case, 3500 volts in another case. L is given as 2 centimeters, that is 2 into 10 power minus 2 meters. D is given as 4 centimeters, that is 4 into 10 power minus 2 meters. And capital L is given as 25 centimeters, that is 25 into 10 power minus 2 meters. And of course, VA is 1000 volts. Now, from this, the formula for deflection sensitivity S is D by VD, that is equal to LLD by 2D VA. That is, L is 2 into 10 power minus 2 to LD is 2 into 10 power minus 2 and L is 25 into 10 power minus 2 divided by 2 into D into VA. Now, if you see here, numerator 10 power minus 4, denominator 10 power minus 3. So, if you do the calculation here, you arrive at the value of deflection sensitivity as 6.25 into 10 power minus 4 meters per volt, or in other words, 0.625 millimeters per unit deflecting voltage in vertical direction. In the second case, when the voltage is 2000, here it is not 1000, it is 2000. Same thing except for a change of 2000 here. Denominator increased by 2, so total value decreases by 2. 6.25 by 2 is 3.125. Third case, 3500. So 3500 here. 1.7857 into 10 power minus 4 meters per volts. This is how you can calculate the deflection sensitivity for different values of accelerating voltages. Another simple example. An electrostatically deflected CRT has plain parallel deflecting plates which are 2.5 centimeters long, LD is 2.5 centimeters, and 0.5 centimeters apart, D is 0.5 centimeters. The distance of the screen from the center of the plates is 20 centimeters. Capital L is 20 centimeters. The accelerating voltage is 2500 volts. E suffix A is 2500 volts. Calculate the deflecting voltage required to get the corresponding deflection of 4 centimeters on the screen and the velocity of the electron beam entering the field. Here the problem is a little twisted. Instead of giving the values and asking for deflection sensitivity, Here the deflection value is given and it is asked to find out the deflecting voltage. D is given as 4 into 10 power minus 2 and L is given as 2.5 into 10 power 2, 20, what is that? LD is 2.5 into 10 power 2 into VD is unknown quantity and capital L is 20 into 10 power minus 2 divided by 2 into D. D is 0.5 centimeters. So 0.5 into 10 power minus 2 into 2500. What is that? It is VA, accelerating voltage. So if you do all the calculations here, you can arrive at the solution as VD is equal to, that is the vertical deflection voltage is equal to 200 volts, which produces a deflection of 4 centimeters on vertical plane. Next, what is the initial velocity of electrons? It is given by the expression 2eVa by m. If we know the value of Va, that is enough to calculate the value of initial velocity. 2 into 1.6 into 10 power 19 by 9.107 into 10 power 31 multiplied with Va, that is 2500. It comes out to be 2.9638 into 10 power 7 meters per second. So that much high voltage, that much high velocity the electron beam attained before entering into the field. So that is all about the deflection and deflection sensitivity and deflection factor. Let us stop here and we'll go to the next topic, CRO controls, in the next class. Thank you.